Okay.
Yeah.
Well, are we all ready to get started then? Okay. All right. Well, thank you. Welcome, everyone. Apologize for some quick technical issues at the beginning of this webinar. I'm Kim Love, and I am the Vice President for Monitoring and Evaluation at the LISA 2020 Network, and I'm also private statistical collaborator in Athens, Georgia. So I am very excited to hear and share today's webinar on 10 common statistical mistakes to watch out for when writing or reviewing a manuscript. So we have some excellent speakers and guests today. And I want to start out by introducing Professor Eric Vance. So he's an associate professor of applied mathematics and also the global director of the LISA 2020 Global Network of Statistical Laboratories. He's also an elected member of the International Statistical Institute, and he's a member of their Statistical Capacity Building Task Force. And I'd like to ask him if he wouldn't mind sharing a little bit about the LISA 2020 network before we get started.
Sure, thank you, Kim. Thank you for all the attendees, especially our distinguished Vice Chancellor, Professor Nazir. Thank you for attending. I will keep my little introductory remarks short. I am the Global Director of the LISA 2020 Network. We are a network of more than 35 statistics and data science collaboration laboratories around the world. And the purpose of the network is to train the next generation of statisticians and data scientists to become collaborative statisticians and data scientists who can move between theory and practice to help people solve problems and make decisions with data. Our goal of the network is to transform evidence into action for the benefit of society. And so we do that by collaborating with domain experts. And so domain experts are welcome to come into our stat labs and collaborate with statisticians and data scientists within the stat labs. And we also teach short courses and workshops. And the point of that is to be able to improve statistical skills and literacy widely in our community so that more people are able to benefit from data, from making decisions with data or transforming that evidence into action for scientific discovery, for businesses, for the social sector, for governmental sector as well. So today we have a webinar and hosted by Professor Imran Khan and also a distinguished speaker of Tonya Esterhuizen from Stellenbosch University in South Africa. So I just want to welcome everybody and kick off this great webinar of the LISA 2020 network. Thank you.
Thank you so much, Eric. And before we go on to our speakers, I'd also like to introduce Professor Nazir Ahmad Ganai, who is the Vice Chancellor at Sher-e-Kashmir University of Agricultural Sciences and Technology of Kashmir. If you wouldn't mind giving us some words of wisdom before we get started.
Thank you, Kimberly, and having me here.
We can hear you.
We spoke, we have heard Professor Eric Vance, who is the global director of this LISA 2020 network. And I am really happy that Dr. Imran has taken steps to include this university as part of this network of 36 laboratories around the world. So I would just say my compliments to Professor Eric Vance, to Kimberly, and to Tonya. I believe that you must have helped Imran to take university to where we are this time as part of this network. The theme of this program, which you have chosen today, the common mistakes which we make in statistics, that is so important for these young scholars, I believe, who are attending us. More than 70 of them are there. And I believe that because they are in research in wherein they want to just wherein they have to just generate the data by themselves, they have to just then lay down those experimental designs correctly, and then have the data, and then manage that data, and then analyze the data, and then interpret the data. So it is a long journey for any graduate student to begin with, but then at the end of the day, when he would be just coming up with his results of his research, those results must be really, in conformity with the facts on the ground, and that depends and stems right from the day he has conceptualized his area of the research. So I will not just go into the details and the depths about the science of statistics, but I will tell to my young students who are attending us that there is no field in life where you don't have statistics. Be it in the making the new discoveries, or what Eric had also said, in decision making, or in making the future predictions. Let me quickly share with my audience, especially the students, telling them that the science, the father of genetics, Mendel, who is the father of genetics, and when he was experimenting with his in his kitchen garden on his pea plants, and he was just trying to cross different kind of pea plants with each other, and he was simply recording the information, the data he was recording, and then there would be a mess of that information. A lot of data he would generate, a lot of data points were available with him. So there was no pattern to that, seemingly. But then what made him to become the father of the genetics, wherein he could ultimately, trace our traits, our characters to the science of genetics, to those kind of, the genes, or the which were unknown till that point of time, was only because he had that kind of an understanding of the science of statistics, or the mathematics, or most probably you can talk about the science of probability, which is a very, very important component of the statistics. So that's how it happened. Had he not that kind of, that analytical mind to correlate those data points, through the science of probability, and would continuously try to find the same kind of a pattern when he would just cross, say, a single hybrid or a double hybrid, or would go with the back crossing. So that helped him to learn, to establish the basis of inheritance of traits. This is just I'm referring to because most of the students who are listening to me are maybe basically mostly from the biological sciences, which they must have heard before. And ultimately, you know that it's about decision making, science of statistics, and then making the predictions. And then I believe that most of us understand that during peak COVID period, when COVID was setting in, when it would emerge from China, and those the very complex algorithms the people in the USA had built for themselves, they would predict right from that day one, when it had not yet struck USA. This COVID had not struck by that time, and they would say that when it would come to USA would say more than 2 lakh deaths. And then, believe me, I heard that first time that the experts say that they have been, building those models, and wherein they have been introducing and including all those variables into it, and then telling the world that we are under threat. More than 2 lakh people would die in America, and everybody, especially in our country, were taken by surprise. How could it happen? But then we could see the death and the disaster it created, and how accurate were those predictions. And then there were waves and waves, and every time, these data scientists would tell us that how is this next wave, going to be like that. So that's where it lies, this science of statistics, and I would wish that they have very, very able and competent experts on board today with us, and please listen to them, listen to their experiences of handling the data, and then deploying them. And you have to build skills by yourself. And let me also share with my friends that this is the a data, age of data, what we normally say that is the fuel of this 21st century, and everything revolves around the data, and billions and billions of data points are generated every single second around the world. See all those online platforms, maybe the e-commerce or anything you do it, and as and when you simply open up your machine or your mobile phone, that something information goes and you don't know, and there are people at the back end of it who are building that information, building that data, and then using that data, and then they're selling that data in this today's age. So I would tell my colleagues that it's very important that you should go into the details and the depths of the data science, which starts with the science of statistics. And let me share with my colleagues who are from this university, if they are listening to me, that we are bringing up a new department of the data science, what we also call as the artificial intelligence and the machine learning center. And wherein we will be needing in coming times guys with very high analytical minds, of course, with the skills they should be having in the computers. So I would congratulate Dr. Imran. I would also congratulate and thank Professor Eric Vance, Professor Kimberly, and Tonya for being with us and going through this session with our students. And I would rather request the panelists and the experts here, please make it a little bit more interactive with the students. And if something could happen, that you could also have their images and pictures on the dashboard, you may feel that you may have that feel of being one-to-one with each other. And I would also appreciate that if at the end of it, we have some kind of feedback or some kind of simple, short kind of those kind of questions you would be putting to them, and trying to understand that how best the participants of this program, the trainees of this training program, have taken it well, and to what extent they have understood the basic theme of conducting this program. And that will encourage us in this university to replicate this program over and over again. And one program cannot do everything. We have to have it in our curriculum. And let me also with my friends that in coming times we'll be just having in this university very short skill programs in different areas, but also in the science of statistics and the maths and then the data science. And the goal is that how do we building the capacity of our students and building their thinking ability and the analytical ability. So with these words, I won't take too much of a time. Thank you very much for having me. Thank you, Eric. Thank you, Tony, and thank you, Kimberly. Hope that goes well with the students. They understand as well. Thank you very much.
Great. Thank you so much, Professor. We very much appreciate your wanting to be here today to help introduce this. All right, I'll go ahead and introduce our speakers today. I'll go ahead and introduce both of them, although I think they will be taking turns speaking. So I'll start with Professor Imran Khan. Imran is working as an associate professor at SKUAST-Kashmir University of Agricultural Sciences and Technology of Kashmir, India. Dr. Imran is a PhD in statistics and has a postdoctorate from the University of Colorado Boulder in the USA. He was awarded the Raman Postdoc Fellowship by University Grants Commission of India. He has an experience of more than 15 years in teaching and research and is the coordinator of the SKUAST-Kashmir University of Agricultural Sciences of Technology Kashmir LISA, SKUAST-K-LISA, and the chairman of the LISA 2020 certificate program. I'll also go ahead and introduce Tonya Esterhuizen. So she's an associate professor of biostatistics, the Department of Epidemiology and Biostatistics. She's a faculty of medicine and health sciences at Stellenbosch University in South Africa. She has an experience of more than 15 years in teaching and research. I will turn it over to, I believe, Imran. Imran, you are muted.
Thank you, Kim.
You're welcome.
Shall I start my screen sharing? Hello, am I audible to all? Kim, am I audible?
Yes, we can hear you.
Okay, fine. Thank you, Kim, for opening up the webinar. Hello, everyone. Good morning, good evening, good day. I welcome you all in this webinar. The main aim of this webinar is to provide reviewers with a tool to identify and manage the common issues. For each common mistake in our list, we discuss how the mistake can arise, explain how it can be detected by authors and or referees, and offer a solution. I will be discussing, since these are the 10 mistakes, I will be discussing 5, and the next 5 will be discussed by Tonya. So we acknowledge Tamar R. Markin for this paper from which we got this idea. The mistakes which arise in the research, they can arise at any stage. Maybe the mistakes can arise at either collection stage, analysis stage, and the interpretation stage. So we need to take care at what stage the mistakes do arise. The 5 mistakes which I'll be discussing is interpreting comparison between 2 effects without directly comparing them, inflating the units of analysis, spurious correlations, correlation and causation, and failing to correct for multiple comparisons. The mistake 1, see, the researchers usually compare, the 2 groups. Sometimes they call them groups, sometimes they call them samples. Sometimes it is drug 1 versus drug 2, or intervention versus intervention second. For these groups, they study the variables. They may study height, they may study weight, they may study yield, etc. So researchers often base their conclusions regarding the impact of intervention, such as pre and post intervention, or a correlation between 2 variables. Based on these 2 separate test outcomes, researchers will sometimes suggest that the effect in experimental condition or group is larger than the effect in the control condition. Now, here we have a small case, one of the cases where the researcher measures 2 variables, X and Y, for group A and group B, and he calculates the correlation coefficient separately for both the groups. Now, for group A, which is denoted by the black circles, and group B is denoted by red circles. So for group A, the correlation is calculated separately with a correlation coefficient of 0.47 and a statistical significance because the p-value is less than 0.05. And for group B, there is no statistical significance. However, if one compares both correlation coefficients, it's possible to find one group, that is group A, denoted by black circles, which has a statistical significance, since the correlation is calculated within the groups, not between the groups. So this does not indicate that the correlation between the variables X and Y between these 2 groups is significant. Now, there is a second case. Maybe we may have 2 groups and it's the intervention case, and we study the pre and post difference between the groups. Now, from the graph as well as from the table, you can see that the researcher has compared pre and post of control and pre and post of the experimental group. You can see the means from the graph, the means of both these are same, but there's a variation. For group D, there is a higher variation than the group C. At the bottom, you will see the p-value for the group C as well as for the group D. That means they have been independently compared. But at the top, you can see the researcher compares group C versus group D. So this means the group C and D, they are same, but the variance for group D is higher. So this doesn't mean that the effect of the intervention is different between the 2 groups. because one should directly compare the groups using independent t-test that we can see at the top of the graph. This shows that this outcome measure is not different for the two groups. But if the researcher compares it on the basis of the individual test, then he can, wrongly say that the group C has a statistical significance than the group D. But in reality, he's not comparing them if he considers the the bottom cases. So the proper way is to compare directly group C with group D. So how do we detect them? This problem arises when a conclusion is drawn regarding a difference between two effects without statistically comparing them. And the solution is the researcher should compare groups directly when they want to contrast them. And the correlations in the two groups can be compared with Monte Carlo simulations. For group comparison on ANOVA, one ANOVA might be suitable, although non-parametric statistics offer some tools. The mistake second, which the researchers commit, is they call the inflating the unit of analysis. The experimental unit is the smallest observation on that can be randomly and independently assigned. In classical statistics, this unit will reflect the degrees of freedom. When inferring group results, the experimental unit is the number of subjects tested rather than the number of observations made within each subject. But unfortunately, researchers tend to mix up these measures, resulting in both conceptual and practical issues. Now, here we can see that we are having 5 experimental units, and every experimental unit, these 5 experimental units, they are observed over 4 weeks of time. Here, the number of observations which we have, they are 20, but the experimental units are only 5. So it's incorrect to take 20 observations as 20 experimental units. This will increase degrees of freedom. Now, how to detect whether the researcher has, there is a mistake of inflating the unit of analysis? The reviewer should consider the appropriate unit of analysis. If a study aims to understand group effects, then the unit of analysis should reflect the variance across subjects, not within subjects. And the solution is we can use a mixed effect linear model. Perhaps the best available solution to this issue, or we can use the repeated measurement ANOVA. This increasingly popular approach allows one to put all the data in the model without violating the assumptions of independence. However, it can be easily misused and requires advanced statistical understanding and should be applied and interpreted with some caution. The third mistake which has been found is it's about spurious correlations. The problem lies with the outliers. So correlations are an important tool in science in order to assess the magnitude of association between two variables. We know the use of parametric correlations such as Pearson's correlation coefficient, Pearson's correlation coefficient that relies on a set of assumptions which are important to consider. As violation of these assumptions, they may give rise to spurious correlations. The spurious correlation, they most commonly arise if one or several outliers are present for one of the two variables. This is an graphics which shows the impact of the outlier, which leads to the spurious correlation. From this graph, we can see single value, which is denoted by a red circle from graph A, B, and C. We have single value, and the single value acts as an outlier, and the inflation, this outlier, the value of the outlier impacts the correlation coefficient. So it's away from the rest of the distribution and can inflate the correlation coefficient. For graph A, the correlation coefficient is somewhere 0.14. Then you can see in the second graph, it's little farther from the main distribution, and the correlation coefficient raises to 0.54. And in the graph C, it raises to again to 0.54, but there is an increase in the confidence interval. Then from group spurious correlation that can also arise from the clusters, which we can see the clusters is from graph D, E, and F. So sometimes if we have groups, for example, group 1 and group 2, and we pool the data of these two groups and take the correlations, it will give us the spurious correlations. So these spurious correlations, they arise from clusters if the data are pooled together when the two groups differ in fact in those two variables. So this is how a researcher can commit if he pools the data of two groups when they are different. So it leads to spurious correlation. Now, how to detect it? So reviewers should pay particular attention to reported correlations that are not accompanied by scatter plot. Scatter plot is it's a beautiful thing if one attaches the scatter plot along with the correlation coefficients in their research papers. So it gives a clear picture whether the correlation is real or it's spurious. In addition, reviewers need to make sure that between group differences are taken into account if data are pooled. And the solutions, as we can use robust correlation methods like bootstrapping or data bin storage, or skipped correlations, because they are less sensitive to outliers. And we should also check the assumptions are violated or not. Then mistake 4 is correlation and causation. So this is one of the oldest and most common problem mistake researchers commit. So while causation and correlation can exist at the same time, but the most common error made when interpreting the statistical results. When two variables are found to be significantly correlated, it's often tempting to assume that one causes the other. For example, we have ice cream sales and woolen products. So decrease in ice cream sales is correlated with sale of woolen products. But it doesn't mean that it causes, the one variable causes the other. They are correlated, but we can't say that one variable is caused by the other. Similarly, it's age and weight. Correlation can't be used as an evidence for cause effect. Now, how should we detect it? Researchers should only use causal language when variable is precisely manipulated. And even then, they should be cautious about the role of confounding factors. And the solution is we should look for the third variable, because now in our case, we were saying that ice creams and woolen products, maybe it's the temperature, in fact, that causes the variables to change. So we need to take into consideration the third variable also. So we should explore the relationship with the third variable that will provide the further support for their interpretation, whether it is really correlation or it is causation. The fifth mistake which the researchers do commit is they fail to correct for multiple comparison. In any experimental design involving comparison of more than two groups or conditions, exploratory analysis will involve multiple comparisons and will increase the probability of detecting an effect even if no such effect exists. A level of significance, which we denote by alpha, that doesn't remain fixed at 5%, which we usually fix at the start of the experiment, or at the start of the research, we fix it at 5%. But when we do multiple comparison, it may inflate. It may go from 5% to 30% for a 2x3x3 experimental design. And by this, we can have more false positives if we go for the exploratory type of analysis. Now, for a comparison of 4 groups or methods, or intervention, or for comparison of 4 varieties, or for comparison of 4 drugs, shall we conduct 6 tests, or we will use only 1 ANOVA? So if we do 6 t-tests for comparing these 4 groups, that means group 1 is to be compared with group 2, group 1 with group 3, and group 1 with group 4. Similarly, other groups with each other. We will be perform 6 t-tests. So whether we should go for 6 t-tests or we should go do only 1 ANOVA. If we do 6 t-tests, we will be having our type 1 error rate that will increase, as we just now saw. It increased from 0.5%. It may go to maybe 20%, or it may go to 30%. Now, how to detect it? A researcher fails to correct for multiple comparisons can be detected by addressing the number of independent variables a researcher measures or studies, and the number of analysis performed, which post hoc test is used, because we are having different post hoc tests for multiple comparison. We have LSD, or we call it a CD, critical difference. We have Duncan's multiple range test. We have Dunnett's test. So we need to decide which test to use when. Exploratory testing can be, so this is the solution. The exploratory testing can be absolutely appropriate, but should be acknowledged. Properly implement the multiple tests, like should we go for one-way ANOVA or multiple t-tests, whether to use planned comparison or unplanned comparison. So accordingly, it will be decided whether to use critical difference or Duncan's multiple range test, or we have many other tests. As I said, we have Dunnett's test, we have case test, so that we decided accordingly. So in my opinion, the single solution to all the mistakes is as a researcher, should consult and collaborate with a statistician. Thank you.
Okay, thank you so much, Imran. We will now switch over to Tonya. Tonya, if you are ready to share your screen.
Okay, thanks, Kim.
You're welcome.
So I hope that you can see my screen. Can you see the title slide and hear me okay?
Yes, we can hear you and see your screen.
Okay, wonderful. Thanks. So thanks, Imran, for giving us a nice start to this presentation by reviewing 5 of the common statistical mistakes. I'm going to continue and look at another 5, again, from the same source. This is the source article from where we got the inspiration. So the 5 problems that I'm going to be considering are flexibility of analysis, or p-hacking, overinterpretation of non-significant results, small sample sizes, absence of a control group, and lastly, circular analysis. I'll start with flexibility of analysis. So as we know, all hypotheses, variables, and analysis should be pre-specified in the research protocol or research proposal. If you want to make any changes to the study on an ad hoc basis, after seeing the data, that's not really a good idea, because obviously your bias on seeing the data can affect any comparisons that you then make. And the more analyses that are added, such as adding more outcome parameters, changing outcomes or covariates, adding more hypotheses to test, etc., all of that increases your chance of a type 1 error, similar to the way that Imran spoke about the last mistake. A type 1 error increases your chance of finding a statistically significant result that does not exist. And in time, that can lead to a systematic bias away from the null hypothesis in published literature. So if many studies are published that have made this mistake, eventually over time we're going to find that the published literature will contain a lot of false positives, which is something that is being highlighted today, that a lot of research findings are actually false. So, p-hacking is a sort of a problem of, that's what we refer to as kind of all of these problems. It's an umbrella term for trying to, adding more tests, changing things, and manipulating the result, manipulating the analysis so that you can find significant results. And then we also get a term called hawking, which is hypothesizing after the results are known. And that's like post hoc hypothesis testing. It's a related concept to p-hacking, and it covers instances when researchers generate hypotheses after the data is collected and test them in the same data set. These hypotheses are more likely to be true and also can lead to higher rates of false positives. For example, an analysis being too flexible is a study that aims to test the effect of BMI on heart failure. BMI is the body mass index. So all of my examples are going to be medical, by the way, but I hope that you guys can all relate. So the researcher did a time to event proportional hazards model, and they found that BMI was in fact not a significant predictor of heart failure, but some of the other covariates that they had used in the model are, like hypertension. So hypertension was one of the variables they found to be significantly related to heart failure. So they removed BMI from the model and only report the effect of hypertension on heart failure. So they kind of forgot that their main reason for doing the study was to look at the effect of BMI, and they sort of changed the hypothesis as they went along based on what the data found. So that's an example of flexibility of analysis. How would a reviewer or somebody who's writing a manuscript or doing research or reviewing a manuscript, how would you detect it? Well, it can be difficult to detect if you don't have the original research protocol available. So that is why it's been quite encouraged that people should publish their research protocols. If you don't have the protocol, you could compare the planned analyses and analyses with those reported. Well, that's if you do have the protocol, because they would state up front what analyses were planned, what the outcome variables were, what the exposure variables were, and what the hypotheses were. But you as a reviewer will have to just exercise good judgment to detect the problem. Now, Imran pointed out that statisticians working with researchers is always a good idea. And the statisticians should always be aware of the original objectives and encourage the researcher to stick to those original objectives instead of coming up with new hypotheses during the analysis phase. So this often happens to me as a consultant statistician. The researcher is disappointed because they're not able to reject their original null hypotheses or prove what they were set out to do. So they always end up trying to add more analyses or beef up their thesis in some way, or the supervisor comes back to them and says, oh, what about this? We've looked at the data and we've seen that there seems to be an association here. Please, can you just look at it for me? Now, the statistician should actually be aware of what is in the protocol and be warning the researcher to stick to the protocol as much as possible. So this figure, the citation is below, but it explores or illustrates the differences between exploratory and confirmatory research. So this is a concept linked to p-hacking and hawking. On the left is exploratory research, where the bullseye is being painted on after the shots are fired. And, this is called, wonky stats. It's not great. It's not good to do that. It's like changing the goalpost after the shots have been fired or after the ball has been thrown. And in the middle is in between confirmatory and exploratory research. And it shows that the data being tortured to conform to some hypothesis. And on the right is confirmatory research with an observed experiment. So although exploratory research is fine and it has its place in research, if it is acknowledged as such, so if you're doing an exploratory study, you need to, say that it's an exploratory research, and you don't try to palm off your exploratory results as confirmatory, because then false positives can arise. So the solution to flexible analyses is, of course, to register your protocols, publish your protocols. In clinical trials, it is required to publish the protocol, or at least to register the trial on clinicaltrials.net or clinicaltrials.org, these registries that we use for clinical trials. And the analysis plan needs to be published. It's pre-specified. Your hypotheses are pre-specified. And so it's more difficult to deviate from something that's already out there in the public domain. Or you could do a replication study to make sure that the previous results are not false positives. Also, journal editors should not focus only on publishing significant results, because authors are forever trying to get something worth publishing, and they think that statistical significance is the only thing that it's going to be published. So they should rather report the true results of the study that they intended, even if it's negative results, and that will prevent to some extent people trying to find significant results and p-hacking. Okay, so the next problem that I'm going to discuss is over-interpretation of non-significant p-values. So the alpha level of 0.05, as we know, it's very arbitrary. If p does not meet this threshold, or so if p is greater than 0.05, it doesn't necessarily mean that there is no effect. What we could have here is a type 2 error due to low power of the study caused by small sample sizes or large standard deviations. A high amount of variability is often present where the sample sizes are really small. So basically it's like, I think it was Douglas Altman said, absence of evidence is not evidence of absence. Finding no significant difference does not mean that there is no difference. It could just mean that your study wasn't large enough to detect a difference that might really be there. So how can one detect it? Well, you might be suspicious if the p-value is not statistically significant, but the absolute effect, such as the difference between two proportions or two means, is large. So that might be one way to look out for it, for an effect size, or for an absolute difference, which you think should be statistically significant, but it's not. And the solution would be to report effect sizes and confidence intervals, as well as p-values, to report the actual p-value, and not just to say p is less than 0.05 or p is greater than 0.05, because that threshold is extremely arbitrary, and we should be, if we're wanting to use p-values, we should report them as an actual probability value, but also to be aware that p-values are not necessarily the be-all and end-all of everything. You can use Bayes factor. which use the data to determine whether non-significant results support a null hypothesis or whether it's a small sample size that faults. Then very much related to the previous problem that I spoke about with non-significant p-values not really meaning that necessarily that there was no difference. The next problem I'm going to talk about is small sample sizes. So as I said, this is very much related. So we know that the distributions of continuous variables in small samples are more likely to deviate from normality than in large samples. And it's also very difficult to test the normality assumption in small samples, because you could get one or two outliers, which could cause invalid results to a greater extent. The effect size estimates from small samples are also likely to be an overestimate. And the power of statistical tests is likely to be low, and the precision as well likely to be low in small sample sizes. So to detect it, we can check the details in the methodology section of the paper for the sample size statements and calculations and formulae that were used. Hopefully reported along with something called the MCID, which is the minimal clinically important difference. So in medical stats, we use clinically important as a benchmark for saying that there is a presence of a difference, an important difference, or an important difference between the groups. And if you're reviewing the paper, to judge for yourself if the sample was adequately powered by looking at the sample size calculation or statement and looking at the sample size that was used and all the other details of the methodology that was used. So also be wary of large claims in small studies. So small study that wants to then say that they have proved something, obviously you're going to be very suspicious. The solution for small sample sizes, obviously that all the details should be shown in the research paper about the sample size and power calculations in the publications or reports. If a researcher has got a very small finite population, often in medicine, that's the case. It's a very, very rare disease or condition that you're studying, and you have a finite population which is very small. If that's the case, you need to provide replications within and between cases and also include sufficient controls. And then, of course, all results from small studies should be interpreted with a lot of caution. So the next problem that I'm going to discuss is the absence of a control group. This is related to one of the problems that Imran spoke about previously. Sometimes you get studies that are designed that they only have one group, but they have repeated measurements on that one group, like a pre and post, or a series of measurements over time, repeated measurements just on one intervention group. And sometimes that's used as a study design to try to estimate the effect of that intervention, even though there's no control group. This can occur when you're wanting to test an intervention where a passive or a placebo control would not be ethical, or it might be difficult to convince participants to recruit into a trial, if it was a randomized control trial, if potential participants were aware that they might be enrolled in an inactive control group. For example, weight training in athletes, you might want to test a certain intervention or certain type of weight training in athletes, and you wouldn't really be able to have a control group because all the athletes should be doing their own weight training, and that might interfere. You won't be able to have a group that isn't doing that weight training. So in these studies, the observed changes in the outcome observed might be due to repeating the outcome measure many times, like a learning effect. So if that outcome measure is, taking a test or something, or performing a scoring protocol, if that participant does it many times over the time of observation, there might be a learning effect. So they're just getting better naturally because of the learning effect. Another reason why changes can occur in health studies, it could be just natural changes in the disease's progression over time rather than due to the actual intervention. So the patient could be getting better over time anyway, regardless of whether they got the intervention or not, or it could just reflect the natural history changes of the disease over time. Also, merely being observed in a study can lead to changes in the outcome, regardless of the effect of the intervention, which is like similar to a placebo effect. Just knowing that you're being enrolled in a study, you can get better just simply because you're being observed, like a Hawthorne effect. So thus a control group is very important to subtract out the placebo effect or the learning effect or the natural progression effect to establish if there is an effect over and above these. So this is just a illustration of what can happen if you have two groups, a control group and an experimental group. And the control group might also show an increase over time in this outcome, if an increase over time is a good outcome. And your experimental group shows this sort of mirroring the control group, but maybe having a slightly higher rate of change over time. One would have to know what's happening in the experimental group to subtract out that in the control group to subtract out the control effect and then look at the effect over and above the control group effect to know if the intervention or the exposure of interest has an effect or not. Otherwise, if you don't have a control group, you can't really talk about the effect of that exposure or the effect of that intervention. If you're just looking at the one group over time, you wouldn't know that it's naturally going to increase anyway without that intervention or without that exposure. So it's easy to detect because obviously you can read up about the design of the study and see that there might not be a control group at all. All the inferences are made based on one treatment group. And people often call it like a self-controlled study. So everybody acts as their own control. They might think, researchers might think that it's a good study design because they're measuring pre and post an intervention and serially over time that you subtract out the sort of baseline effect and you show what you're showing is the effect of an intervention or the effect of this exposure. But in fact, as I've sort of pointed out, it's not necessarily true that you're looking at the effect. You can't actually measure effects that way. And the solution obviously is to build in a control group if you can, if it's possible, if it's ethically possible. Maybe a historical control group if it's not ethically possible to have a parallel control group because there is a treatment available or an intervention that is available and you wouldn't want to deny people from receiving that intervention. So sometimes the historical control group suffices if it's the only solution. If there is no way of having a control group, your conclusions can only be tentative at best. And you would then obviously use this as a sort of an exploratory study so that you can then design a well-designed controlled study to follow this up with so that you can make conclusions from that. Okay, so the last problem I'm going to be talking about is a little bit more complex. It's known as circular analysis, also known as double dipping. So circular analysis has the effect of increasing the apparent association between the exposure and the outcome. And broadly speaking, it occurs where there is non-independence between the criteria used to select the data and the effect of interest. It can occur in various ways. Selection of a specific subset of the data which reflects the effect being studied, or excluding outliers which mask the effect of interest, or different ways of weighting and sorting of criteria on which to base the analysis, which are also linked with the selection or with the outcome. In other words, the researcher's biases or assumptions can affect the results. So hopefully I can show you or demonstrate graphically or pictorially what this, how this occurs. So in A of this diagram, in the top row, it shows that the results of the study should reflect the data. It's often not just a straightforward path from the data to the results. Sometimes and often it's a very convoluted, involved path from the data to the results. And in the top right-hand corner, it shows that our assumptions are often involved in getting in the way between the data and the results, or they contribute somewhat to the results. And then the middle line, or the bottom row of A, or the middle line, shows how the assumptions in red can interact with the data. So this one here, the middle line on the left, is the ideal situation where the results are not contaminated so much by the assumptions. The assumptions are there, but the data is what determines the results. In the middle is the worst case scenario where the assumptions will directly affect the results and the data has nothing to do with it. And in the bottom right is more likely what usually happens in practice, and that is that the data and the assumptions both together will affect the results. And yeah, so that our results are usually a mix of the data and the assumptions. So that is circular analysis, and we need to be able to be very clear about what our assumptions are so that they don't contaminate the results. And then B of this diagram are the three different ways, just try to graphically show the three different ways, or the three most common causes of circularity. Selection is one, weighting and sorting are others. So if the criteria used for selection, weighting, and sorting, if they're not independent of the assumptions or hypotheses, the results will be circular. So the criteria that you use to select or weight or sort your data must not affect or be affected by your hypotheses. How would you detect it? It might be easy to detect if, for instance, the subgroup analyses of a set of data are specifically chosen for showing the effect of interest. For example, if it's in a randomized controlled drug trial and no effect of the drug is found in the population, so you choose a subsample of men over 50 years because you saw that there was an effect in this particular age group. So, that's obviously very problematic. You're choosing your subsample based on where the effect is strongest. To detect unplanned subgroup analyses, you have to then refer to the trial protocol, because if there was planned subgroup analyses, that would be in the trial protocol, i.e. specified before the data is seen. And sometimes it's harder to pick up when reviewing a paper, and you need a detailed understanding of the subject matter. Sometimes you'll see impossibly high effect sizes, and that might alert you to this phenomenon. And reviewers should always try to find out whether the selection criteria and the effect of interest are independent. Of course, the solution is to stick to the protocol, to have pre-planned analyses only, and make sure that everything that you plan to do is in your protocol and that's been published a priori before you've seen the data. And sticking to the protocol in this regard helps to justify that circular analysis has not taken place. Also, one thing that you can do is use two different data sets to define the criteria for subgroups and for testing the predictions. So two different data sets, and that can be done to ensure that your criteria are independent of the results. Also, it can be overcome with bootstrapping and simulation methods without loss of statistical power, because obviously when you're splitting up your data set, you're going to be losing statistical power. But if you use bootstrapping methods, you won't have that problem. So in summary, but most of the problems that we've discussed can be solved by making sure that you have pre-planned hypotheses, pre-planned analysis, statistical analysis plan, a protocol that's very rigorous and published before, and you stick to that protocol and you don't deviate and you don't let your own biases get in the way of the results. Secondly, making sure that you have adequate statistical power can also overcome many of these problems that we've spoken about. So doing power analyses before you do your study, making sure that you can do many other things to increase the statistical power, even if you have a finite small sample size. And then also just knowing when to sort of not do a study if it's going to suffer from loss, too little power, or to declare it an exploratory study rather than a confirmatory study, and not try to do too much with too little. Of course, we always have to keep in the back of our minds to improve the rigor of scientific research, to make research repeatable and reliable, because there's a huge problem in research at the moment in many disciplines, in psychology, in medicine, science, that our research is not repeatable. So we have to make sure that we do replicable research that is well designed and well carried out with minimal bias. So in conclusion, the assumptions of all the solutions that we presented today is that hypothesis testing and p-values are applied and interpreted as actual error rates, which in itself is an ongoing debate. So we advise that you exercise caution when using and interpreting p-values, as they don't have any value unless they're used correctly. And of course, the model assumptions that we're using all have to be fulfilled. Until the body of statisticians in the world has reached a new consensus regarding the best metrics to use in place of the p-value, these methods that we're currently using will have to suffice as long as they are used and interpreted correctly. And on that note, I'll end my presentation and say thank you, and over to you, Kim.
Great. Thank you so much, Tonya. I appreciate both of you giving this presentation, and I think there was a lot of great information. And we did get some questions from the audience. I didn't know if we had time to answer any of those. I have about 3 minutes before I need to leave for my next engagement. Imran and Tonya, would you all be able to answer any of these questions, or is there a way that people can contact you if they'd like to ask or follow up on these questions?
Yeah, there are many questions on this, so I would request the participants to email us so that we can be, we can answer it properly. The time is short. It's not possible to attend all the questions right now.
Okay. All right. Yeah. And then I think we are out of time for today, but thank you everyone who attended. Thank you to our speakers and our guests. And if you have questions that you'd like to follow up with, please go ahead and you're welcome to email our speakers. Any last words before we end for today?
So I would like to thank all who are supported in this webinar, directly or indirectly. Thank you all. Stay blessed. Have a good night, good day.
Thank you, everyone.
Thank you.